All right, so I'm going to try my absolute best to keep this video as short as possible. We're on section 7. Our first blank is a term we've actually already used a few times before. When a point is the same distance from two or more objects, the point is said to be equidistant. The second sentence to this explanation is something you actually haven't learned yet, so just cross this out. Triangle congruence theorems mean nothing to you yet. So moving on. Next, a locus. No, not a locust. It is not a bug. A locus is a set of points that satisfies a given condition. I'm going to use the remainder of this paragraph to actually explain what a locus is, so follow along with me as I do this over here. It says the perpendicular bisector of a segment. So pause. I'll have a segment. I have a perpendicular bisector to it. It should have been a little less squiggly. Meh, good enough. Okay, so this perpendicular bisector is perpendicular to that segment and it bisects that segment. Now, how many points are there on this perpendicular bisector? Hopefully you're thinking infinitely many, because there are infinitely many. Don't tell me 2, don't tell me 1, don't tell me none. I could have infinitely many points on this segment, right? I have the 2 endpoints plus, let's say, this intersection point. I could also put a point here and here, and here and here, and here, and here and here, and anywhere that I see some space. And when I think I've run out of space, I can zoom in and find more space to fill in more points. And then when I think I've filled all of that in, I can zoom in further and fit more points onto that segment and go on in that process forever. So if this segment has infinitely many points, we're going to say that this is going to be actually a locus, a group of points that are equidistant from the endpoints of the segment. So what that means is that no matter where I am on this perpendicular bisector, no matter which point I choose out of the infinitely many, it's going to be equidistant, the same distance, from the 2 ends of the segment that was bisected. This point is going to be the same distance from this point as it is from this point. This here is the same distance from this point as it is from this point, and so on and so on. Any one of those points on that is equidistant to the endpoints of the segment. Hopefully that makes sense, because that's really our summary for these theorems. If I know that I have a perpendicular bisector, in this image here, line L is a perpendicular bisector, right? And if that's the case, I look and realize that point X is on that perpendicular bisector. If that's true, I know its distance from B is equal to its distance from A. Now it works in the reverse as well. We call it the converse. So in the reverse, it says if I have a point on a line that's the same distance away from the 2 endpoints of a segment, then that's enough for me to know that that point was originally on a perpendicular bisector. If you need to rewind and replay that explanation, please do that now, but otherwise let's move on and practice. In this example, I know for a fact I'm already dealing with a perpendicular bisector, because not only is NP perpendicular to ML, but it's bisecting ML. And then I see that point N is on that perpendicular bisector, which means I now know that its distance to L is the same as its distance to M. So NL is 2.6, making MN also 2.6. Good? Great. Next problem. I don't know this time that I have a perpendicular bisector, at least not yet. I see that the 2 lines are perpendicular, but nothing about BD and DC being congruent. What I do see, however, is that point A is equidistant to the 2 endpoints of a segment. That's what tells me that point A is actually on a perpendicular bisector. That's what tells me that the length from BD is congruent to the length between D and C. So if DC is 12, then BD is 12, which means BC is 24. If you're good, turn to the next slide. All right, once again, I look at my picture, I realize I am dealing with a perpendicular bisector, and that perpendicular bisector has point U on it. Point U is equidistant to the endpoints of the segment it's bisecting. So that means 3x plus 9 equals 7x minus 17. Take a moment to solve for that. Pause the video if you need to. In the end, you should find that x equals 6.5. And then we ask, are we done with the problem? Well, no. They didn't ask me for x, they asked me for TU. So TU, while it was 3x plus 9, I now know x is 6.5. So 3 times 6.5 plus 9 winds up giving me a value of 28.5. If you have any questions on that, talk that out with someone around you or come and see me later. Next, looking at my picture, I don't know that I have a perpendicular bisector, but the problem itself tells me that I have a perpendicular bisector. So I already see that these are perpendicular, which means I can now also add in these tick marks to show that that segment was bisected. Which means if that is a perpendicular bisector, I know that this point G on that line is equidistant to the endpoints of the segment that was bisected. So if EG is 14.6, then DG is also 14.6. Moving on, next page. Oh no, don't look. All right, so what I'm looking for you to do next is to work on the next 3 slides. So it's the 2 that are on this page and then the one on the top of the next one. You can pause this video and come back to check your answers. All right, on this problem, hopefully you paused and worked that out. You should have that y is 17, but you were not done. They asked you for FG, and FG, once you substitute 17 in, is 65. If you have any questions, once again, talk to someone near you or come see me later. In this one, you should have found that EG is 8.6. And on the last one, you should have found that EF was 10.4. Once again, if you need help, come see me, please. Moving on to one more theorem in this section. Instead of looking at perpendicular bisectors, we're looking at angle bisectors. The theorem itself sort of works the same though. It tells us that if a point is on the bisector of an angle, so I know I'm dealing with a bisector here because I see these angles are congruent, correct? So ray PC, that's an angle bisector, and C is a point on that angle bisector. So if I know I'm dealing with point C on an angle bisector, it tells me that we know it's equidistant from the sides of the angle. That tells me that if I recall the distance from a point to a line, remember if I'm looking for that distance, I'm not going to hold my ruler any random way. I'm very strategically going to measure the distance that's perpendicular between the point and that line. So notice over here, when they're saying that point C is equidistant to the sides of the angle, they're very specifically talking about the perpendicular distance to the sides of the angle. Those are the measures that are congruent. Now, in addition to that, the reverse is also true. If I see a point and I know it is the same perpendicular distance to one side of an angle as it is to the other side of the angle, I know that that point must have been on an angle bisector in the first place. So let's put that into practice and hopefully be done with this video soon. Find the measure of BC. Well, I know that C is on an angle bisector because of these arc marks, which means it is the same perpendicular distance away from one side as it is to the other. So if CD is 7.2, then BC is 7.2. Next. I don't see that I have an angle bisector, but they do tell me that YW bisects angle X, Y, Z. So if X, Y, Z is getting bisected by YW, I know that these are the angles that are congruent, right? That's the angle that was split into two congruent angles. And what that means is this point W on that angle bisector, well, notice it turned out to be the same perpendicular distance away from X as it is from Z. So if WZ is 3.05, then WX is 3.05. Next page. Here I don't see angle bisector, but I do see that I have point H. And point H is the same perpendicular distance away from two sides of an angle, which means that H must have been on an angle bisector in the first place. So I can acknowledge that angle EFG is split into two congruent angles. Now, if that's true, and I know that angle EFG is 50 degrees, well, that means that angle EFH is worth half of that. So the measure of angle EFH is 25 degrees. Next one. Again, no angle bisector, but I do see that point D is the same perpendicular distance away from two sides of an angle, which means that angle was bisected. And if ABD is 16, then that means ABC is going to be 16 plus 16, or 32 degrees. If good there, turn your page. Find the measure of angle MKL. So in order to find the measure of MKL, I realize that point M is the same perpendicular distance away from two sides of an angle, which means point M was on an angle bisector. So I know that JKL is bisected, making JKM congruent to angle LKM. That means that's my equation. 3a plus 20 equals 2a plus 26. Pause the video here and solve this, please. You should have found that a equals 6, which makes my measure of angle MKL equal to 38 degrees. Hopefully you're good there. Next slide. Pause the video here and please work this one out on your own. Okay, hopefully you had your equation as 2x plus 12 equals 6x minus 18, and you found that x is 7.5. If you did, you found that each angle is 27 degrees, making the entire measure of ABC 54 degrees. Be careful with that. If you have any questions, see me later, please.